We're going to look at three possibilities when it comes to improper integrals. And improper integrals are integrals that have a point that is at least one point, if maybe more, that is undefined in general, and they could be undefined because they have an upper or lower bound that's infinity, or they could be undefined because they have an upper or lower bound that makes the denominator go to 0. So those are some of the ways that we can have undefined upper and lower bounds. And when that happens, we call them improper integrals. And so the first case that we're going to deal with is just literally an upper bound here that is infinity. And so all we do is we say, well, we're going to, instead of having this infinity in the upper bound, we're going to relabel the upper bound b, and we're going to take the limit as b goes to that value infinity. Likewise, we could also have a lower bound of negative infinity, and we're going to replace that with a variable, and then let that variable take a limit as that variable approaches negative infinity. So here's a lower bound that approaches negative infinity. And then for this last one here, sometimes we have both, that it goes from negative infinity to positive infinity, in which case what we do then is we would split it into two expressions, pick a value c that is somewhere between negative infinity and positive infinity, and that value could be 0 if that 0 works in the equations, or it could be some other logical split, and then we would have to go ahead then, and this would fall into a case of the lower bound being going to negative infinity. So this would be a limit as a goes to negative infinity, a to c of f of x dx, or a case 2 from above. And then we would add to that the limit as b goes to positive infinity from c to b of f of x dx. So that would be that expression, and that would be a number 1 from above. As we look at this example here, we have this example from 0 to infinity of x times e to the minus x over 2. And here's the graph of that function. And so we're going from 0 to infinity. And so basically when we're talking about integrating this, we're talking about really finding the area under the curve, right? That's a definition for integration. And so really we want to know if it's finite, the area under the curve is finite, we should get some non-infinite value. We should get some finite value for that integral. If the area is infinite, then then obviously we're going to get some value that's infinity. And so if we're looking at this then says that we have a convergent expression, and this one says we have a divergent expression. And so, if we take a look at this area here, we have to be sure that, as we can see, as our values of x get larger and larger and larger, we have this, what I will call pinching off. In other words, the function is asymptotic here with the x-axis. And so I guess the question remains then, is that pinching off occurring at a fast enough rate to get a finite value for this area? Obviously, if we had something that just kept getting, increasing and increasing and increasing, then this area would be infinite. And so these typical questions always focus on something that is monotonic and bounded. In this case, bounded with the x-axis, and monotonic, where, as for the majority of the values of x, we have this continually decreasing function and this pinching off occurring. So what's left now really is to integrate this. And if we notice on this we can't do a U sub, this happens to be an integration by parts sort of problem. So just kind of a sneaky way of working in an integration by parts, just as a refresher. And so we know that an integration by parts is a power reducing exercise. Remember back to integration by parts. And so we need to have an expression for U that is the simpler of the two. Kind of a rhyme there, but really it's meant to reduce the power on one of the pieces of the product. And then the dv is typically the more complex expression, so in this case e to the minus x over 2 dx. And then so getting the expression then for du is just dx, and getting the expression then for v, integrating this, we're taking, of course it's e to the minus x over 2, but then we have to take the reciprocal of this, and the reciprocal of negative 1/2 is negative 2. So we have to put in a negative 2 there. And then we can set up our integration by parts, which says u dv equals u times v minus the integral of v du. And like I said, if we look at this, the du now is that expression, it's that power reducing. So u times v is x times e to the minus x over 2. And the integral of v du is this times that, so that's minus 2e to the minus x over 2 dx. And so really all I'm doing is I'm going through the integration part as if we were just in the integration by parts section, which is, what is that? That's section 8.2, I believe. And so I haven't really talked about the indeterminate issues here. I just want to get through the integration first on this problem since it is a little more complex. So to finish out the integration here, we're going to go ahead and integrate that. And as we integrate that, we already have integrated e to the x over 2. It's right here. And so I'm going to pull out the minus 2, so minus 2 with another negative is a positive 2, and then integrating e to the minus x over 2 is right here, so we have another minus 2e to the minus x over 2. And so we have this integral, this answer, excuse me, that looks like, get rid of the plus sign there. There we go. Minus 4e to the minus x over 2. Okay, so so there's our just our refresher on integration by parts. So let's talk about the indeterminate question itself. We're going from 0 to infinity. So we're looking at the integral from 0 to infinity of x e to the minus x over 2 dx. And so here's our indeterminate limit. So we want to take the limit as, I'll just call it b. B goes to infinity. And then I'm going to replace that upper bound with b. And so we have an expression that looks like that. So we're going to take the limit as b goes to infinity of this integral. And so we've evaluated this integral, it's this. So really what it means is that we're taking the limit as b goes to infinity of this expression. And that's why I wanted to get the integration set up ahead of time, because I can just plop it in then and worry about evaluating the limit without muddying the waters with the integration. So we're taking the limit of this expression. This expression integrated is this, the lower bound is 0 and the upper bound is b. And so as we evaluate that, the limit as b goes to infinity, we're talking about b, it's kind of sloppy, let me get rid of that. We're talking about b times e to the minus b over 2 minus 4 e to the minus b over 2. That's the upper limit. And then the lower limit is 0 times e to the 0 minus 4 times e to the 0. And you always want to be sure when you're dealing with Euler's number, even if the lower limit is 0, to plug that in, because well, e to the 0 is 1. So, you know, in this case, this portion of that lower limit doesn't drop out. So you can't just eliminate or ignore that lower limit when it's 0. So as b approaches infinity here, we have to evaluate that. And so as b approaches infinity, you know, this is really b over e to the b over 2, and minus 4 over e to the b over 2. That's what the negative exponent means. And this is 0 minus 4. And so as we're evaluating this, as b goes to infinity, this grows faster compared to this. So this whole thing goes to 0. Likewise, since this is constant, this goes to infinity, this goes to 0. This is 0. So what we have left, after we evaluate as the limit as b goes to infinity, we have 0 minus 0, which is 0, minus a negative 4. So we have a limit of 4. And so since we get a finite limit, and that literally is the area under the curve. So the area under the curve is 4, and since it's finite, we can determine that this actually converges. And really converges is kind of short for the phrase converges to a finite value. In this example, again, we're looking at, and again, I always think it's very effective to kind of graph this to see what we're looking at. But again, we have that characteristic pinching off that's occurring here. And that's all we're doing is we're checking the area under this curve here for a finite value. And if we get that finite value, that means we're pinching off fast enough. And that is really how we determine whether or not we have a convergent or a divergent expression. And as we get into the next chapter, we're going to be able to quantify what fast enough means. But for right now, we really don't have a good feel for what fast enough is, other than if we get a finite number, it is fast enough. And if we don't get a finite number, if we get infinity, it's not fast enough. And but we'll actually be able to nail that down and put a number on it in the next chapter in this book. But for right now, we're just looking for that finite value. So that area here is actually the value of the integral. And so again, we're looking at this. We have a lower limit of 1 and an upper limit of infinity. That's the indeterminate portion of this expression. So I'm going to go ahead and just kind of set up the expression for integrating this, and worry about the improper expression and how to evaluate the limit after I get this answer for the integration. So the fourth root of x can be written like this when it's in the denominator, and so it's a power rule here. So we're just going to go ahead and take bump this up by 1, so adding 1 to this gets us 3/4, taking the reciprocal gets us 4/3, x to the 3/4. So when we integrate this, we get 16/3 x to the 3/4. So that's the integral of that expression. And so what we're looking at is the expression from 1 to infinity of 4 over the fourth root of x dx. And so I'm just going to call that upper limit b again. And so we're going to take a limit as b goes to infinity of 4 over the fourth root of x dx. And so that is the limit as b goes to infinity of 16/3 x to the 3/4 from 1 to b. And so if we evaluate that, then we get the limit of when b goes to infinity of 16/3 b to the 3/4 minus 16/3 and 1 to the 3/4 power. And of course 1 to the 3/4 power is just 1. And if you notice that when we put in infinity and take infinity to the 3/4 power, now we're cubing infinity and taking the fourth root, we're still going to end up with infinity here. So we end up with infinity minus 16/3, which is still infinity. And so since we do not get a finite value, we don't get a finite value here, we must have a divergent expression here. We say that this integral is diverges, or that this problem is a divergent problem. So taking a look at this in terms of pinching off, we can see that there's still a whole hunk of area here, and this pinching off isn't that dramatic, especially when you compare it to this pinching off, which was far more dramatic. So this pinching off was fast enough, and this pinching off is not fast enough. So coming back up here, fast enough, we'll add a little question mark there. The answer is no, it's not fast enough. And that's why we have this infinite area, here.